Hi, I thought I would share something I just root caused at home, but it really brought up an interesting point regarding trying to solve an issue when you understand what the potential root causes could be, just because the technology is understood, versus not. Because I was able to solve the issue, but I realized as I was doing it, if I didn't already know what the root cause was, it would have, or potential root causes could be based on how the mechanism works, it would have been incredibly difficult to figure out. So to me, this emphasized quite simply the importance of when you do really good reliability testing, root cause analysis, and understand your failure modes when you're doing design, it can make all the difference in solving a field failure. So what is it? This is a circuit breaker. You're probably very familiar with it. You have them in your electrical panels at home. This one I marked bad. One of the reasons why I did is because it looks to be in like new condition, because the wear out failure mode doesn't really induce any visible issue, even internally in a lot of cases. This one is for my furnace, and it's probably been there a very long time. It's probably even gone through more than one furnace, just about, because they will last so long. Now, a circuit breaker is effectively a reusable fuse. If you probably know what an electrical fuse is. When there's too much amperage in a circuit, the fuse opens the circuit, usually by destroying itself, and it protects everything else in the circuit. But a circuit breaker does this and can be reset. You reset the switch, the circuit's closed again. And then if the amperage exceeds the rating, where on here it's 15 amps, it will open up again. So how does it work? Let's take a look at how it works. So what we have is a contactor here, which when we actuate the switch, I have to try and do this without it falling apart and visible to you with the cover off. Let's see, there we go. So now we've closed the circuit. The one lead coming in would be here and the other would be back here. Now you see there's this path of the electricity. And what we have here is a bimetal strip. Now, bimetal strip, two different metals with two different thermal expansion coefficients. So when it gets hot, it will flex. So it effectively will move when it's hot, and it's carrying amperage through it. So when the amperage gets high enough, it works as a resistor, gets enough heat, and it will actuate the, let's see if I can do it backwards. So when it moves a little bit, it'll actuate and open the circuit. So look at this thing. It looks perfect, right? It looks brand new. It's an enclosed case that's riveted shut, so it doesn't see oxidation generally, unless it's in a very humid environment. So if I was to try and understand what's wrong with this, it would be very difficult. Even the bimetal strip looks to be in great condition. So first thing, when the circuit breaks, that doesn't mean it's broken, right? That's its job. It's what it's supposed to do. So at home, be careful. If your circuit breakers go off, don't just change your circuit breaker, because that's probably not the issue. It's probably doing its job and there's over amperage somewhere, you should understand. But in my case with my furnace, it kept going off. And so we went through the furnace, we had it maintained. It actually was rebuilt not that long ago. There was some soot and some things to clean up, but it didn't make sense. There's nothing else on the circuit, and there was no reason that the furnace would be pulling greater amperage, which brought me to the circuit breaker. Now, again, knowing that they can wear out over time, it was worth investigating and trying now that we knew that the furnace wasn't pulling too much amperage. So we simply replaced the circuit breaker with a new one, and the problem was solved, and we know it's not pulling too much amperage. It was the circuit breaker. It was this one. It had worn out. It takes a very long time for them to wear out, and this one could have been in there for, who knows, 15 years or something. But what actually wears out? Well, what actually in this case had worn out was the bimetal strip getting heated over time had changed some of the material properties to where it would, under lower amperage, bend enough. It's a very sensitive, it's almost like a mouse trap here, very sensitive. That's a spring. The bimetal strip's actually here. Very little motion, it'll flip. So if this was a new product that we had designed and was in the field, would I have thought that the material properties had changed in the bimetal strip enough to do that? That would have been a pretty long investigation and would have been very difficult if I was handling units that had just failed in the field in our new product. But what if in the product development program, I'd done testing and caused failures by running extremely high amperages over and over and over again to see how it would wear out. Not that it worked the way it was supposed to, because obviously your design works the way it's supposed to. But what if I did a lot of cycles of really high amperage, kind of in that, highly robust, the robust ready principle, using some Hall testing to cause it to happen over and over again, find out what those levels are, and then use them for stress margin testing, and effectively wearing out the device prematurely, root causing it, understand what that is, and keeping a record of that. If you knew that, you would have been able to solve this issue, even with new technology, as fast as I was, because I had the knowledge, because these have been used for many, many decades. And to anybody who plays with home, home repair, knows that that is something that could be the case over time. So I just thought that was a really interesting example and further justification for investing in reliability testing to understand failure modes early in your product development program.